Hi guys, so we're going to talk about the process of chromatography as part of the core practical in the edexcel 9:1 specification of investigating inks. Now edexcel don't consider chromatography on its own as a core practical, but they pair it with another process called distillation. But because you need to know quite a lot about both of these processes, each one deserves its own video. So I'll do chromatography now, and then in a second video, we'll go through distillation. Just to give you a basic overview of what chromatography is, scientists use chromatography to separate a mixture. So the mixture that we will be separating is ink. Ink is a mixture of lots of different chemicals, but they're not chemically bonded together, so they're fairly easy to separate out. Chromatography can also be used to analyze a mixture. Once the components of the mixture have been separated out, we can use chromatography to work out what is in the mixture. As part of your core practicals, you're likely to be asked questions from one of three possible areas. Either what's the method of the core practical and how do you carry out the investigation? Or what are the results and why do you get the results that you do? Or finally, they could ask you about scientific knowledge that explains why you get the results you do. So for that reason, I'm going to break this video up into three sections, starting off with the method. For paper chromatography, we don't need very many pieces of equipment. We're going to need a beaker large enough to put a piece of chromatography paper in, a piece of chromatography paper, which is essentially filter paper that's cut into a strip, a splint, paper clip, some sort of lid to put on top of the beaker, a ruler, a pencil, and distilled water. That's all we need. So there's nothing particularly dangerous here, but I'm going to wear eye protection anyway, just in case, because it's not unsafe for me to wear the goggles, so I might as well put them on. So we're going to start by preparing the piece of chromatography paper, and so you guys can see what I'm doing, we're just going to zoom in a little bit more on the paper. To begin with, we need to draw a starting line on the piece of chromatography paper. The starting line has to be drawn in pencil. We never use ink to draw on the piece of chromatography paper, because if I did a start line with ink, then that would run up the paper as well, along with my sample. The start line, we should use a ruler, and it doesn't really matter where we go, but we're going to want a little bit of a gap at the bottom, so just a few centimeters up from the bottom, and I'm going to draw a start line as straight as I possibly can. That is called the origin line, and that is where I'm going to put small spots of my different inks on that line. So this is going to be the first pen ink that we are going to analyze, and I'm just going to put a small spot, nice and neat, on my origin line like that. This is a different pen with possibly a different type of ink, so I'm going to do exactly the same on the origin line, a nice small neat spot there. The final ink that we're going to analyze is going to come from this ink cartridge. So I'm just going to very carefully dab a little bit of ink onto the start line to produce a small spot. Now my inks are on my origin line, I'm going to use a pencil to label my inks as the first ink, second ink, and the third ink. Another word for the piece of chromatography paper is the stationary phase, because during the separation, the piece of paper doesn't move. The other phase that we talk about in chromatography is the mobile phase, which is the liquid that we are going to allow to wash up the piece of paper. Now, in our chromatography investigation, we're going to use distilled water, not tap water. That's because tap water has got things dissolved in it that could interfere with our results. We know that distilled water is pure water. Another word for the mobile phase is the solvent, because it's going to dissolve some of the chemicals in the ink. And a solvent is a liquid that can dissolve other chemicals. The solvent is going to go into the big beaker, but it's really important that I don't add too much, because the water cannot go above these dots here and the origin line on the piece of chromatography paper. Because if it did, then all the ink would just wash off of the paper and into the water in the beaker. So I'm going to use my piece of paper here as a little bit of a guide, and I'm going to put the water in very slowly. Now the water's at the level that I want it to be at, I'm going to make sure that my piece of chromatography paper doesn't move around whilst the chromatography separation is happening. So I'm going to use this splint and I'm going to roll it around a few times on the piece of chromatography paper, and I'm going to use the splint to hang the chromatography paper in the beaker like clothes on a washing line. And I'm going to lay that into the beaker. I'm also going to put a lid on the top so that it stops any dust or anything that could be floating around in the room possibly getting onto the piece of chromatography paper and affecting our separation. Now, when the chromatography is happening, it's really important that we don't touch it, move it, or jog it, because that's going to cause the inks to start moving as they go up the page, and they're all going to end up running in with each other. So once the lid's on, we now need to leave it and let the water soak up and wash over the ink spots. Once the inks have separated out on the paper and I've drawn the solvent front line, this is now called a chromatogram. And there are a few things that we can do to analyse the inks that we've just looked at and separated. First of all, if we look at the colours and the pattern of the chemicals that have come from ink 1, we can see that they are identical to the colours and the patterns that have come from ink 3. Therefore, we can say that ink 1 and ink 3 are basically the same mixture. Ink 2, on the other hand, looks completely different. Ink 2 does not have the same colours or pattern of spots moving up on the piece of paper. So we can say that ink 2 is a different ink. From each of these spots that we've got on our chromatogram, we can calculate something called an RF value. The formula for the RF value is one that you will need to remember because you're unlikely to be given it in the exam paper. The formula for the RF value is the distance moved by the spot in centimetres divided by the distance moved by the solvent, also in centimetres. All of these measurements need to be measured down to the origin line and never the bottom of the paper. So I'm going to measure the RF value of this yellow chemical here on ink 1. And I'm going to start by measuring the distance that the yellow chemical moved from the start line. Now that looks to have moved about 6.6 centimetres. So we're going to say that the distance moved by the spot is 6 by 6 centimetres. Then I'm going to measure the distance between the two lines that I've drawn on here. So the distance between the solvent front and the start line. And I get a value of that one of 6.9 centimetres. So to calculate the RF value of just this yellow spot here, I would do 6.6 divided by 6.9, and that comes to a total of 0.96. There are a couple of things to know about RF values. One of them is that they are never greater than 1, because an RF value greater than 1 would mean that one of these colours has moved beyond the solvent, which obviously can't happen. So if you try to calculate an RF value and it is 1 or greater, you know you've done something wrong with the calculation. Secondly, we usually give RF values to 2 decimal places, so we would need to round up the second number after the decimal place. And thirdly, RF values do not have any units, they are just a number. The reason why RF values are so important is because they make our chromatograms reproducible. If we was to have a second chromatogram to compare, and if we look at this one, we can see that if I line up their origin lines, we can see that this one was left for a little bit longer and the colours have gone up a little bit further, but so has the solvent as well. So if I measure the RF value of this yellow spot, we can see that this yellow spot has moved up about 6.8 centimetres and the solvent moved up about 7.1 centimetres. So if I was to measure the RF value of the yellow spot on this chromatogram, then I would do 6.8 divided by 7.1, which also comes to 0.96. So even though colours have moved up by different amounts, they are still chemical because they have the same RF value. That's why it doesn't matter how long you leave the piece of chromatography paper into the water, or it also doesn't matter how long your piece of chromatography paper is, as long as you've left the water in there long enough so that you can see that the colours have separated, but not too long, because you don't want to let the water touch the top of the piece of chromatography paper. So now we should know how to carry out chromatography as a process for the investigation, and also be able to use the chromatogram to analyse the inks and calculate the RF value. The final thing that I want to take you through is the science behind why the colours separate out in the ink. And to do that, we're going to need to use our imaginations. The main scientific principle that explains chromatography is solubility, or how well the different chemicals in the ink dissolve in water. Remember that I said that ink is a mixture of different chemicals. Some of these chemicals will be very soluble in the water, and they will want to stay in the water as much as possible when the water washes over them and will run up the paper at a fast speed. Other chemicals in the ink are not very soluble at all, and they hate being in the water, so they will want to stick to the paper as much as possible. These chemicals then have to be dragged up the paper with the water and will move much slower than their more soluble chemicals. In fact, if a chemical is totally insoluble, then it will stay on the origin line and not move at all. When the water washes over the ink chemicals, the different chemicals will divide their time between being in the water and sticking to the paper. When they are in the water, or the mobile phase, they move up. When they're sticking to the paper, or the stationary phase, they don't move at all. Of course, the chemicals do not divide their time equally between the two phases. The more soluble the chemical is, the more time it will spend in the mobile phase, which is why it moves faster and therefore further than less soluble chemicals. In fact, the most soluble chemicals love being in the water so much that they hardly ever stick to the stationary phase during the separation, so they practically move up with the water at the same speed. Given enough time, all of the chemicals would eventually reach the end of the paper and mix up again. This is why we stop the process before the water reaches the top, to stop this from happening. If you like, a chromatogram is like a snapshot of a race, where the most soluble chemicals always win and the least soluble chemicals are at a huge disadvantage.